So, for our first application of bound states, I want to take an example that has some important technological implications. And these implications have a lot to do actually with modern communication technologies. In modern digital communication, we have these fiber optic networks. And the way they work is you have semiconducting lasers that take electronic signals, right, and transform them into light signals. And then we send that light down fiber optic cables. And part of the design of the system is to make sure that the frequency of the light that comes out of the laser is very closely matched to certain special frequency bands in the fiber. In particular, frequency bands where the losses in the fiber, the absorption of the light, is at a very low minimum value. This way we can have very long cables before we need to put in new repeating stations where we download the light, reprocess it electronically, and then send the signal back along the cable, which leads to then latencies in the internet. So to reduce this and to allow us then to tune the light to those very special frequencies, we use devices that are known as quantum well lasers. And I'm not going to go into, all of the finer details of the operation, but I wanted to give you a sense of what the material structure looks like and how it directly relates to the kind of quantum mechanics we're doing, and how actually the kind of quantum calculations we will be doing allow us to tune the frequency of the light that come out of these devices. So a quantum well laser is a device. It's made out of a material, right? And it's a sandwich of materials. So first you have a big thick piece of bread, if you will, and that bread is made out of a material which is aluminum gallium arsenide. And then there's a relatively thin layer, which makes up what's called the quantum well, of just pure gallium arsenide. And then it goes back to a thick layer of aluminum gallium arsenide. And one of the really remarkable technological achievements of our age is that we can actually grow very thin and very well-controlled interfaces between materials like this, where in fact this interface can be atomically sharp, where you have one unit cell of the aluminum gallium arsenide crystal on this side, and then you go to perfect on the next row of atoms gallium arsenide crystal on this side over here. Now, how this relates to what we've been studying is we can think about the potential energy that electrons feel in this material sandwich. So if I were to plot then the potential, and I will center my axes right in the middle of this middle layer here. So I'm going to be plotting then along here the potential of x as a function of position x. And the potential looks as follows. The electrons have different potential energies in different materials. So throughout the aluminum gallium arsenide, there is one value for my potential V of x, like so. And then, when I go into the gallium arsenide, there's a sudden change in the potential. And that potential changes very quickly, literally over the distance of a single atom, which is actually fairly small compared to the wavelengths of the electrons in this laser. So, therefore, we can regard this as a discontinuity in the potential to a new value. And that new value in here, I will, because I can choose my zero of potential to take on any value that I like, I will call the potential of electrons in gallium arsenide 0. And so then the height of the potential in this aluminum gallium arsenide, I will call that parameter V0. When I take my next atomically sharp step back into the same aluminum gallium arsenide, of course the potential then jumps up again to the same value that it had originally. So this height here is now V0. And you can see I basically have a stepped potential with two different steps in it. A step down by V0 and a step back up. To give you more of the additional parameters in this problem, I will make the width of this distance 2 times a. So this step down interface occurs at x equals minus a, and this step up potential occurs at x equals plus a. Now, the idea behind how this works is that there are certain bound states for the electrons within this confining region called the quantum well. So I'll have some energy like so, E0, say this is the lowest energy. And you can see it will be a bound state. because its energy is less than the potential at large distances. And because it's a bound state, I know I'm expecting some amount of spacing between the next available state, and I'll call that next state that might occur here E sub 1. And the way then that this device operates, I'm skipping some of the details for you, but basically the way that this device operates is that electrons come in, right? And when they enter into the device, they enter in with energy E1, and then at some point in the process, through this lasing process, there is a transition in their energy where the electrons make a transition from this energy level E1 to this other quantum state E0. And when that transition occurs, then we know photons will be emitted as the electrons give off their energy. And that photon energy has to match the change in the energy of the electrons, which would then equal this E1 minus E0. So what we're hoping that we can do is we can take known material parameters for the potential energy of electrons in either of these two different materials, so we will know what V0 is, and then our job will be to learn how to find out what these energies are so that we can engineer in a purposeful way that by changing this distance A, we want to learn how these energies relate to that distance A, so that then ultimately we could choose an A that will tune this energy difference to give us photons of exactly the frequency that we would like. So our job then really is to understand the behavior of electrons in a potential that has this general form. Now, this is the form of the potential that corresponds to this quantum well laser device. There's also a standard name for this potential. This is known as a finite square well. It's called finite because the potential out here in this forbidden region has a finite value, so it's a finite square well. It's called a square well because it has somewhat of an appearance of a square. It's a well, but it has these sharp, discrete edges, and just for your information, frequently when we refer to this potential, I might abbreviate it FSW. So our job now then is to analyze the solutions to the time-independent Schrödinger equation in this type of a potential environment.